Well, good afternoon. It's 12:17 on Wednesday, the 4th of November, 2020. It's supposed to be Calculus 3 class, but right now I'm the only one here, so I guess I'll go on and get started. Don't know where the others are. I just checked to make sure that the invite went out, and it indicated it did, so I'm assuming that others will be coming in soon. I'm going to start from the current slide, and I wish you were here I'd ask you, are there any questions? But there's nobody here, and this is rather unusual because usually y'all are here about the same time I'm getting cranked up. So I just don't. Let me check one more time and make sure there's nobody waiting. There's nobody waiting there. And let's hold off on this for a moment. Let me go back to and make sure that the announcement did make. Blackboard is so awkward. There it says 5 posted, 5 total. And one of them is today. So I'm in the right class. Everything's here. Let me just look at it and make sure. Yep, 12:15, and it's now 12:19, so we're 4 minutes over. So everything looks good. I just don't know where everybody is. All right, we'll go back to here. And we are recording, so I guess we'll go from this point on. This is really unusual for a class of this size, 8 students, and have no one showing up. That indicates to me there's a problem with the system, but I can't see where that problem is now, so I'm going to just have to go from there. Last time we started section 11.6. This is the last section in chapter 11 that we're covering. We're not going to do 11.7. So when we finish today, I'll probably post out there for you the chapter 11 test. So now, I don't know. Let's go on and get started. Chapter 11 is vectors in the geometry of space. 11.6 is surfaces in space, and we have talked about cylindrical surfaces last time, and then last time we started with quadric surfaces. That's where we're picking up now. It says how to sketch a quadric surface. So it says to classify and sketch the surface that's 2x squared minus 3y squared plus 12z squared plus 12 is equal to 0. All right. Now, that was a mouthful, wasn't it? Let's see the characteristics we pay attention to here. Number one, what I would do first on a problem like this is set it up this way. 4x squared minus 3y squared plus 12z squared is equal to a minus 12. Subtract 12 from both sides. Now, divide everything by a minus 12. A minus 12, a minus 12, and a minus 12. Okay? Now, what does this give you? X squared over, now this is going to seem a bit strange to do it this way, but the square root of 3 squared with a minus out front, plus y squared over 2 squared minus z squared over 1 squared, and that's equal to 1. Now, why did I do it that way? Okay, to sort of get it into our standard form. Okay, now what does this tell us? Okay, if you go back to the illustrations we did before, remember, if all these were pluses, right here, 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 and of course there, then that would have been an ellipsoid. If all the constants here were the same, that would have been a sphere. A sphere is a special case of an ellipsoid. They're not, okay? 2 of these are negative and 1 is positive, okay? Now, when you see that, the one that's positive is going to wind up being the one that's your main axis here, okay? Now, anytime you have a quadric surface with all squares there, it's either going to be a sphere, which we've ruled out, an ellipsoid, which we've ruled out, and the only other option is an hyperboloid, because to be a paraboloid, one of those has to be to the first power. It's not. All of these to the squared power, the second term, the second degree. Okay, so that means this is going to be an hyperboloids. Okay, now the question then is this a hyperboloid of 1 sheet or 2 sheets? Okay, now this probably isn't the best way to think of it, but it's how I think of it. Okay, if you'll turn back a page, you'll see that the hyperboloid of 1 sheet has 1 negative sign. The hyperboloid of 2 sheets has 2 negative signs. So this makes this, the first thing says to classify it, so the classification here is hyperboloid of 2 sheets. Okay, because you have 2 minus signs there. And that's why it was important to get this to be a +1 to see what happens there. Now, hyperboloid of 2 sheets, the one odd sign out, the plus sign here, that means that's your axis. Okay, now it's 2 sheets now. That means at plus and minus 2 on the y-axis, that's going to be your vertices, you might think of them. Oh, here comes Jemanuel. So good to see someone showing up here. Okay, Jemanuel, where is everybody else? Do you have any idea? Okay, can you hear me yet? Oh, and here comes Kira. This is making me feel a whole lot better. Okay, usually this class is very close to perfect attendance, and I was here all by myself. Okay, is anyone else in the wings out there waiting? Nope, just the 2 of you. But I'm glad y'all are here. Very glad y'all are here. Okay, do y'all have any questions, issues, concerns? Did you have a hard time getting in, or were you just running late, or I couldn't tell. Everything looked good from my end, but yesterday myself and other students were having problems getting in. I blame some of that on the election day. I thought everybody in the world was on the internet. Not quite, but close. And perhaps today, since there's still counting and verifying and stuff, maybe everybody's still out there. Did y'all have particular problems getting on the system? Yes or no? Oh, okay, good. Okay. All right, so hopefully others will be coming in too, and it looks like maybe one is coming in now. I don't think so, though. There was a chat or something here. I don't know if I can get to see it here. From Jemanuel to everyone, no. So I take that to mean you didn't have any trouble getting here. Okay, good to hear. Okay. Now, my memory was, and my marks were, that we were about to do example 2 on page 802, chapter 11, Vectors in the Geometry of Space, 11.6, Surfaces in Space. We had already done cylindrical surfaces, and we had started doing quadric surfaces, okay? And here was example 2, and since y'all, neither one were here to begin with, it says classify and sketch the surface, okay? I'm trying to find, oh, there's my pen, okay. Lost my pen here, okay. Now, how I go about classifying this surface, I rewrite this in what I considered more of a standard form, okay? And here's what that standard form was. 4x squared minus 3y squared plus 12z squared is equal to minus 12. In other words, subtracted 12 from both sides. Now, I don't like ending with a negative sign, okay? I want that to be a positive 1. So the next thing I did was divide everything by negative 12. Now, that makes this 4x squared over minus 12 minus 3y squared over minus 12 plus 12z squared over minus 12 is equal to negative 12 over negative 12. Okay, that moves the minus sign here, x squared, and I just chose to write it as square root of 3 squared. Okay, because 4 going to 12 3 times, but I want this to be a perfect square. And 3 is the perfect square of the square root of 3. This one would have been plus 3 over 4, or 4 is the perfect square of 2, so that would be plus y squared over 2 squared, and then this one was just minus 12 over 12 is 1, so minus z squared over 1 squared. And that left us a plus 1 here, which is exactly what I wanted. Now here's where, and if you go back and listen to this, you'll hear it again. Here is where we have to decide how to classify this. This is sort of our standard form here, but how do we go about classifying it? Well, as I mentioned before y'all came in, anytime all your exponents are 2's, that's a dead giveaway that you're either dealing with a sphere. A sphere would have all pluses here, not any minuses, and it would have all the same number down here. These are not, so this is not a sphere. If it was an ellipsoid, these would all be pluses here, but they wouldn't necessarily be the same numbers down here. All spheres are ellipsoids, but not all ellipsoids are spheres. Now, that leaves only one other shape that has all 3 quadratic variables. Sorry. Okay, and that's an hyperboloid. Okay, so that gave us the hyperboloid part. Now this was the sort of silly little rule that I go by, and you can flip back a page or two and look at it and you'll see. If you have one minus sign, that would give you a hyperboloid of 1 sheet. If you have 2 minus signs, that gives you a hyperboloid of 2 sheets. Now, why can't this be a paraboloid? Because with a paraboloid, one of those variables has to be to the first power, not to the second power. Okay, so that narrowed it down to a hyperboloid, 2 minus signs, so that gives you 2 sheets. Now, the odd man out, the one that's not, in this case, the only positive one, that means that has to be the axis of this hyperboloid of two sheets. Okay, so the y-axis is going to be the axis of this. Now, we haven't been dealing with any where you have other numbers in here. You could, and if you did, then that's going to change your center of the object. This is x minus 0 squared, y minus 0 squared, z minus 0 squared is centered at the origin, 0, 0, 0. Okay. Now, especially for this one who is the axis here, this means that plus 2 and minus 2, that's why I wrote it as 2 squared here, those are going to be the two vertices that are on the y-axis. Y is equal to plus 2, y is equal to minus 2. So we've already started our sketch right there. So what I'm going to do, my sketching is terrible. I'll admit that. Okay, so let's get y. Okay, here we go. That'll be my z-axis, that'll be my y-axis, and this will be my x-axis. Okay. Oh, and here comes Kyle. Okay, we're gradually increasing our numbers here. Okay, so Kyle is here. So the top of, oh, I see. Practice or game? Yeah, okay. I know how coaches are. Okay. Didn't ever play baseball, but I played football, basketball, so they always go long, or sometimes do anyway. Okay, what we're doing is example 2, top of page 802, chapter 11, vectors and geometry of space. 11.6 is surfaces in space. Last time on Monday we started this section and we dealt with cylindrical surfaces and got into quadric surfaces. It was really exciting if you remember correctly. And now we're doing actually sketching a quadric surface, which is really exciting stuff to do. Okay, so I don't sketch these things well. Three-dimensional shapes and on two-dimensional board, not an easy thing to do. This is the x-axis, this is the y-axis, this is the z-axis. Now, it doesn't have to be drawn this way, but it does have to be drawn in some type of right-hand rule. Okay, so you point your fingers of your right hand in the x direction, bend it to the y direction. The z is going to be your positive z direction. Okay, so I dotted the lines in for a negative x this way, negative y that way, negative z that way. All right, now just had explained to the others how we go about classifying this. First, I rewrote, this was the equation they gave us. I rewrote it by subtracting 12 from both sides, and so I have 4x squared minus 3y squared plus 12z squared is equal to minus 12. I don't like having a minus 12 here. I want a positive 1 there. So I divide everything by minus 12. Every term by minus 12. Now that is going to produce a negative for the x squared, because 4 over minus 12 is going to be 1 over 3. Have the x squared by itself. Okay, and this should be, pull the minus sign on the outside, and then this would be 4 will go into 12 3 times. 3 is the perfect square of square root of 3. Here we have our positive 3 minus 3 over minus 12 would be a positive 1 over 4. Well, 4 is a perfect square of 2. So write that as y squared over 2 squared. And this one, 12 over minus 12, would be a minus 1 z squared over 1 squared. That's a little crazy to write it that way, but I do just to emphasize that. And then this negative 12 over 12 is 1. Now, as I said before, if you have all three of your variables raised to the second power, okay, quadratics, okay, then you're either going to have a sphere, an ellipsoid, or a hyperboloid. Got to be one of those three. For a sphere or ellipsoid, all three of the signs have to be plus. understanding that this one's a plus. They're not, okay? So that rules out spheres and ellipsoids. Now, that leaves your hyperboloids, but you have two types of hyperboloids. One is a hyperboloid of one sheet, and one's a hyperboloid of two sheets. Count the number of negative signs, okay? You have 1, 2, so that's going to be hyperboloid of two sheets. If you only had one negative sign, then that would be hyperboloid of one sheet. Okay, the odd sign out, that's your plus sign here, that means that's going to be the axis, and that's going to be on the y-axis. Now I'm going to start drawing in, if I can find my pen. Where did it go? There it is. Okay, let's count off 1, 2 on the y-axis, 1, 2 on the y-axis. Minus here, so a positive that way. That's going to be the vertex of your hyperboloid of two sheets. Okay, now what that leaves you with is, if you ignore the z for now and have y squared minus x squared, basically here, I'm forgetting the things down here, that gives you hyperboloids in the xy plane. Okay, so that's going to be something like this in the xy plane there, and something like this in the xy plane there. Sorry about that. Okay, if you do the same for the x, ignoring the x's here, and you have y squared minus z squared here, then you're going to have hyperboloids in the yz plane. Okay, and again, these are really hard to figure out how to draw them, okay, because it's hard to see which plane you're in. But this basically gives you, and then if you ignore the y, then you have x squared plus z squared. Those are, they're both minus, factor out the minus, and that gives you ellipses like this, okay? And that really is ugly here, okay? But these would be ellipses as you get bigger and bigger and bigger, okay? Now, those are really awful looking, but that basically is how you do your sketching, okay? Do your traces in every dimension, okay, and go from there. So let's see if they can do a little bit better job than I do in the drawing, okay? Now, I think I'm going to have to erase my scratch so you can read a little bit more easily what they're doing. Begin by writing the equation in standard form. To me, that's not standard form, okay? This is the original equation. So writing it in standard form is going to be subtracting the 12 from both sides. Oh boy, okay. They didn't subtract 12 from both sides. They just divided everything by 12. No, minus 12, which is ultimately what I did, but I saw that by subtracting 12 from both sides. So I don't like the way they did it, but it's okay. Okay? You're almost the same thing we have. You divide everything by minus 12. Just out of the blue they did that. Okay? And then add 1 to both sides. I would have subtracted 12 from both sides, then divided by minus 12, and that's how we wound up here. Now, what they also did was rearrange the order here. And they didn't take square roots here. I like to do the square roots there. Okay? You can conclude that the surface is a hyperboloid of two sheets, with the y-axis being the axis for that hyperboloid. Okay? Now, we got there the same way, but they just concluded that. Comparing to the other, I gave you my little rule. The odd sign out, that's your axis, so that would be the y-axis, and the fact that you have two minus signs, that makes it a hyperboloid of two sheets. Okay, because if you ignore the z here, that's a hyperbola. If you ignore the x here, that's a hyperbola. And if you had ignored the y here, that would be an ellipse. So that's your shapes in all three traces. So to sketch the graph of this surface helps to find the traces on the coordinate planes. In the xy plane, that's where z is equal to 0, you get hyperbola, okay? And this is plus or minus 2 here, plus or minus the square root of 3 there. In the xz plane trace here, where y is equal to 0, that gives you, they say no trace, okay? No, in the xz plane, there is no trace because this is positive, that's negative. Can't happen, okay? A positive number cannot be a negative number. However, if you go out to y is equal to 2 or minus 2, then you have things that you can do traces. They won't be in the xz plane, but you can do traces in planes that are perpendicular or parallel to the xz plane. And then the third one is the yz trace. That's where x is equal to 0, and again you get a hyperbola there too. Those are the ones I was trying to draw in and doing a really lousy job of it. Okay, so let's see what we've got here at plus 2 and minus 2. They don't even mention that here. They should have. Okay, at plus 2 and minus 2, those are your vertices. Here's your y-axis. That is the axis for this hyperboloid of two sheets. And then you have your hyperbola in the xy plane here, and your hyperbola in the yz plane here and here. Okay, so that gives you your hyperboloid of two sheets. They don't go to great extent to describe to you how narrow or whatever it is. I will point this out to you. The z being a plus or minus 1 and the y being a plus or minus 2, that makes it in the, oh, here comes Houston. Good deal. We're finally getting a good sized class here. We've got half of our students here anyway. And even though Jemanuel started pulling in the bottom half of the alphabet and was the only one here, now the top half of the alphabet is outweighed him 3-1. So hopefully the others will be coming in too. So Houston, we're here in chapter 11, Vectors and the Geometry of Space, in section 11.6, Surfaces in Space. And last time we started with cylindrical surfaces and moved on to quadric surfaces and just sort of got the introduction of those done. Now we're doing example 2 on page 802, which is sketching the graph of a quadratic surface, of a quadric surface, which you really didn't want to see my graph, but this is it here. You'll have to go back and watch the things, but this, they gave you a form that was not standard form. You manipulated that until you got into standard form, and because all three of your variables are squared, that means you had to have either a sphere, an ellipsoid, or a hyperboloid. Those are the three that have squareds for all three of your variables. A paraboloid, one of those three has to be to the first power. They can't all be squared. Okay, so that's that. Now, the number of positive signs, that lets you know whether it's a sphere or ellipse. If all three of these signs were positive, if the denominators were all the same, you have a sphere. If the denominators were not all the same and all signs were positive, you have an ellipsoid. Now, if only one sign is positive, which we have here, two are negative, then you have a hyperboloid of two sheets. If one sign was negative and the other two were positive, you have a hyperboloid of one sheet. The odd sign out, this one is the positive sign, this gives you your axis of that hyperboloid. And you see the y-axis is the axis for that hyperboloid. 2 sheets here because of that. And as they sort of pointed out to you, in the XZ plane there is no point of intersection, because in the XZ plane y is 0, and you'd have a negative numbers here, positive number there, can't happen. So in the XZ plane, which is the plane here, x-axis, z-axis, no point of intersection. Okay. In the other 2 planes you have hyperbolas. Okay, y squared minus x squared and y squared minus z squared. Those are both hyperbolas, and those are the traces in those planes. And that pretty much shows us how to draw our graph. All right, any questions so far? Okay, if I could get this to advance. They're skipping example 3, 4. Oh, here comes Esther. Good deal. We're now over 50%. And, well, I can't write with my ionizing pen. The top half of the alphabet is now perfect attendance. Way to go. And the bottom half of the alphabet was just the first student here, which was Jemanuel, and he's the only one holding up the bottom half of the alphabet. So hopefully the others will be coming in too. All right, Esther, we were just commenting, we had just done example 2 on page 802. They are skipping examples 3 and 4. We're going to do those next, and then we'll start the surfaces of revolution. So I'm trying to get my slideshow to go back, and let's go to our whiteboard. Okay, now since it's the first time we've been in whiteboard today, I've got to move some things around. You can't see these, but they put a toolbar here that covers a lot of white space. I don't want that to happen. And they also move it over so your names and things like this cover part of the white space, and I try to minimize that. So that's about the best I can do. I think you probably only see a white screen. So let's do example 3. Classify and sketch the surface. Okay. X, that should ring a bell right there, minus y squared. I can't get this thing to draw. Okay. X minus y squared minus 4z squared is equal to 0. Okay. Now, it says classify and sketch each surface. Now, number 1, that's the z squared. Okay. Number 1, when you have one variable to the first power, the other 2 to the second power, that gives it away. This is a paraboloid. Okay, so we know it's a paraboloid. Okay, now that's all we know so far. It's a paraboloid. The second part says, is a paraboloid a hyperbolic paraboloid or is it an elliptic paraboloid? Okay, now what's going to give that away? Okay, now if you go to the previous page, you'll see the pictures there. The elliptic paraboloid has ellipses as your traces, okay, parallel to your axis. Okay, now, okay, time out a moment here. You know here that the axis of this thing has to be the x-axis, okay, because that's the 1 to the first power, okay. Now, if you recall, the sphere, ellipsoids, and hyperboloids, all with squares everywhere, a sphere has no axis to speak of. Ellipsoid, really, I mean, it does have some axes. The longest axes are the one with the largest denominators, okay? And the smallest axes are the smallest denominators, okay? So you can sort of orient them that way. As we just saw in your hyperboloids, it's the odd sign out, okay? That's your axis for your hyperboloids. With your paraboloids, it's the linear one out. The other two are this. So if you rewrite this, you would rewrite it as x is equal to y squared plus 4z squared. Okay. You added these to the other side. Okay. What does this describe for you? That describes an ellipse. The square terms are here, both of them being positive. That has to be an ellipse. So that basically makes this an elliptic paraboloid. Now, I didn't leave enough room to write this in, but let me try it. Elliptic paraboloid, okay? Because your right hand side are the same signs, and that makes for an ellipse. If they were opposite signs on the right hand side, that would make it a hyperbola. These are the same, so they're ellipses. Okay, now that's how you classify. Let's see how we draw. Okay, now again, my drawings are really awful. Okay, there's your axes, the x, the y, and the z. However you draw them, make sure you follow the right hand rule. Point your fingers of your right hand in the x direction, positive x direction, fold them in the positive y direction, and your right hand thumb is pointing in the positive z direction. Okay, so I'm going to also sort of draw the negative x-axis here, the negative y-axis kind of there, and the negative z-axis down here. Okay, now that supposedly gives us our space. Okay, it's still two-dimensional. Okay, now let's take z equals 0. So that's going to be the xy plane here. Well, this will be x is equal to y squared. Okay, so x is going to be positive whatever the y is. So that's going to be that is your parabola in the x y plane. Okay, now let's do the other one. Let y be 0, and that gives you the xz plane, and in the xz plane, which is this plane over here, this is so hard to draw. There is your parabola in the xz plane, like that. It's a vertical stretch, okay? And your ellipses, when x is equal to any constant, when it's 0, of course that's 0, but any positive constant here has to be positive, can't be negative. Nothing can be over here because these are both positive. That has to be positive. Then these are your ellipses that are formed like this. Okay, really ugly drawings here. Okay, there is your elliptic paraboloid. Okay, now, oh, I was wondering, why does it not look that way? If you look in your book on page 802, bottom figure there, you'll see indeed that's what you got. My shape is pretty lousy, okay, in many ways, but you get the general idea of it. If you can get anywhere close, you're in good shape there. All right, that was example 3. Any questions on example 3? Okay, let's then clear this and go to example 4. Okay. Now this, they're going to do something really evil to us. they are having a shape that is not centered at the origin. Okay, they basically said they weren't going to do this to us, and now they've turned around and done it to us. Okay, if you go back to quadric surfaces, they say here on page 799, in the table on the next few pages, only one of the several orientations of each quadric surface is shown. When the surface is oriented along a different axis, its standard equation will change accordingly. Well, I thought they were going to say it here. But basically, all their figures they showed on page 800 and 801 were basically kind of centered at the origin. Okay, example 4 is not going to be that way. Now, if you go to larsoncalculus.com, you can see an interactive version of this type of example. So here's what we're asked to do. I'm going to have to put the book in my lap because these are hard to read. Okay, here's your surface. X squared plus 2y squared plus z squared minus 4x plus 4y minus 2z. This is such a pain in the neck. It erased my 2. I've got to sneeze. Sorry about that, folks. Plus 3 is equal to 0. Now that's how they gave it to you. That is anything but a standard form. Okay. Now, I hope I've got all the signs right because it was erasing stuff as I went. Okay. I believe that's correct. All right. Now, what it says to do is classify and sketch the surface. Okay. So we've got to get it into some sort of standard form. Here's what my suggestion to you is. Get all your variables together. Okay. So the first thing I'm going to do here is do my x squared minus 4x. And I'm going to leave a blank there. And then I'm going to do plus 2y squared plus 4y. And leave a blank. And then I'm going to do a plus z squared minus 2z and leave a blank, and then move the plus 3 over and make it a minus 3. Alright, now that doesn't look particularly good, but you see everything is accounted for. Okay, now what's the next thing I'm going to do? Complete the square. That's why I left the blank. And if you remember fondly, I'm sure, how to complete the square of a quadratic, okay, type form here, take half of the b term, that's the linear term, half of negative 4 is negative 2, square it. So that's going to be a plus 4. Negative 2 squared is plus 4. I've just changed the problem. I added 4 here. So I better change the problem by adding a 4 here as well. Okay, now it's balanced again. And I left off my square here. Okay. The next thing I'm going to do, well, I'm going to go on and do this. As soon as you take half of that b term, that gives you x minus 2 squared. Okay. Now, next I'm going to factor out this 2. I sort of hate that it was even there, but we've got to factor it out, so let's factor it out. 2 times y squared plus 2y, right? Factoring out 2 out. Blank. and this will be fine. I'll leave that alone for now. Well, I want to complete this square. Well, half of the 2 is going to be a 1, plus 1, square it, and you get a plus 1 here. But there's 2 on the outside, that means I just added 2 here, so I'd better add another 2 over here as well. Okay? Now, this already has a 1 as a coefficient, so I don't have to factor anything out, and this is going to be half of your b term is going to be half of -2 is -1, square that, you get a plus 1. So this would be z squared minus 2z plus 1. Well, I just added a 1 here, so I better add a 1 over here too to keep everything balanced. So what do we have now? X minus 2 squared plus 2 times y plus 1 squared, we completed the square, plus z minus 1, as soon as you take half of this, you got it, and squared is equal to, and what did these add up to? 4 and 2 is 6, 7 minus 3 is 4. Alright, now that's still not standard form. I want to divide everything by 4. Divide everything by 4 on both sides of the equation. Okay, now what does that give us? X minus 2 squared over 2 squared. I like to have a square in that denominator. Plus, let's just make this a y plus 1 squared over root 2 squared, because 2 will go into 4 twice, and to get that to be a perfect square, now that is real ugly there, so let's see if I can clean that up a little bit. I'll just erase it all. That cleaned it right up, didn't it? Okay, so this will be y plus 1 squared over root 2 squared plus z minus 1 squared over 2 squared, and that's equal to 1, which is exactly what I wanted that to be there. Alright, now what did all this do for us? Well, number 1, this tells us what kind of a is going to classify it for us. Remember, all 3 of these variables, the x, the y, and the z, are all squared. So that means it's either a sphere, an ellipsoid, or hyperboloid. Because if one of them was not squared, that would have been a paraboloid. So we look then at our signs. All 3 signs are positive. If I can find my, oh, there it is. Positive here, positive here, positive there. That means it's either a sphere or an ellipsoid. Okay? Those are all going to be positive. If it was a sphere, all 3 of these numbers would be the same. It's not. These 2 are, that one's not, so this is going to be an ellipsoid. Now, what about these things here? The x minus 2, y plus 1, z minus 1, this identifies the center of that ellipsoid. X equal plus 2, y is equal minus 1, z is equal to plus 1. So, if I were drawing my axes, which I'm not drawing very well here, obviously, okay, so this is x, y, and z. I already started drawing my negative z down here, my negative y over here, and my negative x back here. Okay, so we go 2 out on x, we go 1 down on y, or back on y, that would be back here. So that would be somewhere about here, and then go up 1 on z, so go up here 1 unit on z. There is the center of that ellipsoid. Okay, now what else do we know? We go plus or minus 2 here to the vertex on x, so that goes plus 2 in this direction. There's another 1, 2. Minus 2 would be 1, 2, so you're back here on the z-axis kind of there. Plus or minus 1 on the y, and that would be plus this way 1 and back this way 1, and then plus or minus y, I'm sorry, said that wrong. It's the root 2 that you're going, plus or minus root 2. So that would be plus root 2 here, that's 1.4. Minus root 2 would be negative 1.4, and then plus or minus 2 on z, which would be, goodness, I can't even find my center again, somewhere plus 2 and minus 2. That would be our ellipsoid. Okay. Okay, something like that. Okay, really ugly. I told you, mine really stink. And if you look at the page 803 in the book, you'll see basically how you get that. Classified as an ellipsoid because all of your signs are positive. All your radicals are positive 2. I mean, all the exponents are 2, and your the denominators are not all the same. 2, 2, and root 2. If those all three have been a 2, then you would have had actually a sphere rather than an ellipsoid. A sphere is a type of ellipsoid that has all dimensions being the same. This one, the x and y dimensions are the long dimensions, and the x and z dimensions are the long dimensions, and your y dimension is your shorter dimension. And that's pretty much what you see there. A pretty good looking Easter egg in some senses. Okay. All right. There is a little technology blurb here at the bottom of page 803. You're certainly welcome to look at it. I don't have Mathematica, so I can't do that for you. Okay. Now, any questions on quadric surfaces? That's all we got, folks. Let's talk a little bit about surfaces of revolution. This isn't something that was in your course description. Cylindrical surfaces were not, only quadric surfaces were. So let's just go through these pretty quickly and not spend too much time on them. Let's go back to the PowerPoints, and we'll go resume the slideshow. I want to say slideshow, but that's not quite right. And now let's go surfaces of revolution. Again, we're going to do this fairly quickly. Let's see what happens. The fifth special type of surface you will study is a surface of revolution. Now, what were the earlier ones? They had spheres, planes, cylindrical surfaces, quadric surfaces, and now surfaces of revolution. Okay? You'll now look at a procedure for finding its equation. So let's consider the graph of the radius. I'm sorry, my throat is really beginning to hurt, and let me get a sip of something here. I don't know if it helps, but the carbonation makes it feel a little better. Okay. We'll now look at a procedure for finding the equation of a surface of revolution. Let's consider the graph of the radius function. Okay, y is equal to r of z. Okay, now Y is a variable, Z is a variable. R is your radius function, okay? So this is going to be a function in the YZ plane. So that's what gives that away, okay? Meaning X is not going to enter the picture here directly. I'll put it that way, okay? Which means, of course, something parallel to the x-axis is probably going to be the axis of this shape, okay? No, not quite, okay? When that graph is revolved around the z-axis, so obviously it's the z-axis that is the one of interest here, okay? So that's the variable of the radius function. Excuse me. It forms a surface of revolution, okay? The trace of the surface in the plane z is equal to z0. That's somewhere up here in the z-axis. Now, to me, that's beginning to look a lot like a Hershey's Kiss, which I think in terms of food, okay? When the trace in the surface of the plane z is equal to z0, that's some value here, z0, okay? Okay, the trace of the surface in that plane is a circle whose radius is that r of z0. I'm sorry, my throat is hurting like crazy. And whose equation is x squared plus y squared is equal to that r squared. That's your standard form for a circle. X squared plus y squared is equal to r squared. Now, is that something for me, or y'all communicating among yourselves? Okay, if I need to see it, let me know. Go on and blurt it out, unless it's something you don't want me to see, but if I were to pull it up, everybody would see it. So, sorry about that. Okay. Okay. So every one of the traces in the plane, z is equal to any z0, is going to be a circle, okay? And so what this makes it a surface of revolution around that axis, and this happens in this case to be the z-axis. Now, it says replacing z0 with z produces an equation that's valid for all values of z. So when you had a z0 in there, that gives you just that little circle there. Let z vary from, say, 0 to wherever, infinity, then you've got the surface of revolution that's there. Okay. In a similar manner, you obtain equations for surfaces of revolution on the other two axes, and those results are summarized below. If the graph of the radius function r is revolved around one of the coordinate axes, then the equation of the resulting surface of revolution has one of the forms listed below. If it's revolved around the x-axis, then your yz, leave off the one you're revolving around. Yz plus y squared plus z squared is equal to some radius of x squared. If it's revolved around the y-axis, it's yz, xz plus yz times the radius of, as a function of y squared. I'm sorry. It's getting harder and harder to talk. Hold on. And if it's revolved around the z-axis, like the one we just saw, it's x squared plus y squared is equal to that radius as a function of z squared. Those are your surfaces of revolution. Now, without doing too much on this, let's just see if we can sort of talk our way through it. Find an equation for the surface of revolution formed by revolving the graph of y is equal to 1 over z about the z-axis. Okay? Now, The first part of this, because you're doing about the z-axis, is going to be x squared plus y squared. Okay, that's the easy part. Okay, now x squared plus y squared is equal to, and then that function of z, here it is. So that would be 1 over z squared. Okay, because that would be your radius squared. So x squared plus y squared is equal to 1 over z squared. 1 squared over z squared. Okay, let's see how that panned out. There is your radius function is 1 over z. When you're revolving around the z-axis, that would be x squared plus y squared is equal to this. The radius function is a function of z squared, which would be x squared plus y squared is equal to 1 over z squared. Okay, now if you wanted to, okay, they don't want to, they're just going to leave it like that. Okay, how about this one? Find the equation of a surface of revolution formed by revolving the graph of 9x squared is equal to y cubed about the y-axis. Okay, now you want the y the other variable expressed in terms of y, just like here we had y expressed in terms of z. So here, since it's the y-axis, you want the x expressed in terms of y. Okay, so let's do that. I'm so sorry. That would give you x is equal to y cubed over 9. Okay, x squared is equal to y cubed over 9, and then take the square root of that, and you get x is equal to plus or minus the square root of y cubed over 9. Okay, I guess I should go and write that down. Okay, solve for x. So aggravating, my clip keeps falling off my pocket. Okay, so we have x is equal to plus or minus, and since we're taking a square root, let's make it 1/3 of y to the 3 power. Okay, see if that works. If you square both sides, that gives you x squared is equal to 1/9 of y cubed, and multiply both sides by 9. Yeah, I think that works. Okay, so now that's your function. That's the radius function right there. That's the radius function. So what you would have then would be x squared plus z squared, the other two variables, is equal to sorry, 1 over 9 times y cubed. Okay, because you have the square of that. So that, I think, is what your surface of revolution would be. Let's see if we can find it. Okay, and that's what I got. X squared plus z squared is equal to 1/9 y cubed. Let's see if that's the same thing I wrote. X squared plus z squared is equal to 1/9 y cubed. Perfect. Okay, and there's your megaphone. Okay, there's the graph of that. And weird shape, but perfectly good. Okay, I think that is the last slide in the section. Okay, They did have a example 6, and we could do it if you want to. It's up to you. Do you want to do example 6? Example 6 is a little different from the other 2, okay? But if you're happy with it, we don't have to do it. What you want to do? Yay or nay? Okay. I don't know why they did example 6 the way they did. So I'd say let's leave it alone. Homework exercises here would be these. Do your concept check, okay? 1 through 4 or 1 and 3, whatever they have. I don't know if those are at Calc Chat or not, but I think they should be. Then on 5 through 10, I would try to match all 6 of those, okay? Only the answers in the back end at calcchat.com are given for the odd ones, but I think you should be able to pick out and match which of these shapes you see here correspond to the equations you see right below them. Then do either 11 or 13. They're both at Calc Chat. 11's at Calc View. Any of the odds 15 to 25, they're all at Calc Chat. 17's at Calc View. Either 27 or 29, both at Calc Chat. They should be anyway. And then any of the odds 31 to 35. They should all be at Calc Chat. 31 should be at Calc View. 37 or 39, they should both be at Calc Chat. 37 should be at Calc View. 41 should be at Calc Chat. 43 should be at Calc Chat. 45 should be at Calc Chat. 47 should be, well, I'd say any of the odds from 47 through 51 should be at Calc Chat. Okay. Now, I'm all in favor of skipping 11.7. That's cylindrical and spherical coordinates. Would you think it would be good for you to at least see the slideshow on that, even if you're not going to be tested on it, or are you all in favor of going on to 12.1? What would you like to do? You want to see the slideshow 11.7? You're not going to be tested over it, but just in case you ever need it, you would know how to get to it you'd have some clue of how to get to it. So what do you want to do, 11.7 or 12.1? Anyone have an opinion? Have I put you all to sleep? Anybody? Are you still there? Anybody? Okay. I can't tell. I see Esther's name on the board, but it's only showing 1, so I don't even know if the rest of you are present. Say we've got 5 students, and yes, we do have all 5. Do any of you have an opinion? Do you want to see the slideshow for 11.7 or go on to 12.1? Not a sound from anybody. Okay. How are we doing on time? Okay, we got plenty of time. So what I'm going to do, since y'all aren't responding, I'm going to get out of this slideshow. I'm going to try to get out of the slideshow. Discard what I'm using now. Get out of 11.6 and see if I can find how to get to 12.1. There it is. So y'all didn't give me an opinion, so I'm going to 12.1. Okay, I'm going to move my toolbar, taskbar out of the way here, and we'll start with current slide. Okay, now time out just a moment. Hopefully sometime between 4 and 6 this evening, I will get you your chapter 11 test. I believe I've got it made out already. If I don't, I'll have to make some adjustments to it. But I think, well, I've just got to see. Okay, I taught this last summer. I think I have that test already made out. If I do, we'll be in fine shape. If not, it may not be there today. It may be a little bit later. So you've got your chapter 11 test coming to you sometime soon. Okay, so let's move on and get into chapter 12, vector valued functions. Okay, so we're going to skip 11.7. I couldn't get a response out of you then. Let me give you this though, in the review exercises beginning on page 815. These may be some if you need a few more to practice with. All the odds are at calcchat.com, so you can do number 1 if you'd like, number 3 if you'd like, number 5 if you'd like, number 7 if you'd like, number 9 if you'd like, number 11 if you'd like, number 13 if you'd like, number 15 if you'd like, number 17 if you'd like, number 19 if you'd like, 21 if you'd like, 23 if you'd like, 25 if you'd like, 27 if you'd like, 29 if you'd like, 31 if you'd like, and then I would say either 33 or 35. Okay, is that some? Oh, here's James. Good deal. All right, let me get James marked here. We finally have the top 6 here. Don't have Jesus or Laurent. Hopefully they'll be coming in sometime soon. Now it's 1:29 and we go to 1:55, so they don't have a lot of time, but they do have some time. James, we just had finished 11.6, and I gave them the option, did you want to see the slideshow on 11.7? No one responded at all. So I skipped 11.7 and was just giving some additional problems. If you want to, need some more to look at in the review exercises on pages 815 and 816. I just had said either 33 or 35 are at Calc Chat, 37's at Calc Chat, 39's at Calc Chat, 41 or 43 should both be at Calc Chat, and then any of the odds 45 through 47 should be at Calc Chat, 49 through 57 should be at Calc Chat. You can hang off on the rest of those, the surfaces of revolution, though we did do some of those, and then the converting rectangular coordinates to either cylindrical or spherical, and vice versa. You can do them if you'd like, especially if you think your major will be dealing with those. There is a problem-solving section on page 817 to 818. You can certainly look at any of the odds for that there at calcchat.com as well. Now, that leads us to Chapter 12, Vector Valued Functions. Okay? Now, I can't get it to advance. Okay. Section 12.1 is also named Vector Valued Functions. The chapter name and the first section name are the same. In 12.1, what we're going to do, our objectives here are to analyze and sketch the space curve given by a vectored value function. We'll extend the concepts of limits and continuity to vector valued functions. Now, what in the world do we mean by vector value function? Well, on page 820, they began the presentation here. My thing keeps falling off my pocket. It's such a pain in the neck. Okay. we're starting with space curves and vector value functions. Let's get some definitions and concepts down. Now, a plane curve is defined as a set of ordered pairs f of t, g of t, together with the defining parametric equations, the x is equal to f of t, y is equal to g of t, where f and g are both continuous functions of the parameter t on some interval I. Now that's a plane curve. That definition can then be extended naturally to 3 dimensions in space. The space curve, capital C, okay? They didn't give a name for the plane curve, okay, but they do give it for the space curve. Capital C is a set of all the ordered triplets, f of t, g of t, h of t, together with their defining parametric equations, x equal f of t, y is equal to g of t, z is equal to h of t, where f, g, and h are continuous functions of your parameter t on some interval I. Okay, now notice they're continuous functions. You can't have any gaps, holes, spaces, or things like this. It doesn't say they have to be differentiable functions. Later we'll specify that as well. But right now, any continuous functions of the variable parameter t. Okay. Now, a new type of function is called a vector valued function is introduced here. This type of function maps real numbers into vectors. Okay? The real numbers are your values for your t, and your vectors are now the, usually given the term r of t, but that is now a bold r, meaning you're dealing with vectors. Okay? And in this case, the t, remember, is your parameter, a scalar number, and you have a scalar function here, f of t, that's your x coordinate is your f of t, your y coordinate is your g of t, and the f of ti plus g of tj, that gives you your vector function, vector valued function. Or in 3 dimensions, that's in a plane, in 3 dimensions in space, that r of t would be f of ti plus g of tj plus h of tk, where again, your f, g, and h are scalar functions, but they are the coordinates of your vector your unit vectors in the I, j, and k, the x, y, and z direction. Those are your vector value functions, where the component functions f, g, and h are real valued functions. They're scalar functions. They're not vectors themselves of that parameter t. The vector valued functions are sometimes denoted this way. R of t in the plane would be f of t, angle bracket, f of t, comma, g of t, close angle bracket. Or in the space, r of t would be open angle bracket, f of t, comma, g of t, comma, h of t, close bracket, close angle bracket. Those are your components of a vector. Okay? Components of your vector. Technically, a curve in the plane or in space consists of a collection of points and the defining parametric equations. Okay? Now, 2 different curves can have the same graph. Okay? So here's some examples of that. R of t could be sine of t I plus cosine of tj. Okay? That's going to be basically a circle of radius 1. Okay? Now, unit circle. Or if you did r of t is equal to sine of t squared I plus cosine of t squared j, all that you're doing now is squaring the t first and making the components of I and j, sine of t squared I cosine of t squared j. that also has the unit circle as its graphs, but those equations do not represent the same curve because the circle traced out in different ways on the graphs. Okay, now we'll see that a little bit later. They kind of jumped the gun on you a little bit here, but it does work. That what they're saying is true. Okay, be sure that you see the distinction between the vector value function r and the real value functions f, g, and h. Okay, the vector value function has components of a vector. The real value functions f, g, and h are those components of the function. All r functions of the real variable t, but r of t is a vector, whereas f of t, g of t, and h of t are real numbers, scalar values of those functions. Okay, real value functions are sometimes called scalar functions. I've been calling them that all along to distinguish them from the vector value functions. Okay, a lot of blah 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 at the first of this chapter. Vector value functions serve dual roles in the representation of curves. Okay, by letting the parameter t represent time, you can use the vector value functions to represent motion along the curve. Or, in the more general case, you can use a vector value function to trace the graph of a curve. Okay, so either it represents motion along a curve or to trace the graph of a curve, which almost sounds like the same thing, but there is a subtle difference. In either case, the terminal point of the position vector r of t coincides with the point xy or xyz on the curve given by the parametric equations as shown here. Okay, I'm sorry, I'm going to have to get a little more caffeine here. Okay. Now, here is a curve in the plane, the xy plane. Now, there's no three dimension here, it's just the xy plane. Okay. When t is equal to t0, your vector function is f of t0, y of t0, g of t0. Okay, that gives you an f function here, a y value there, and that's somewhere negative on x, positive on y. Sometime later, t equal to t1, you're also in the plane, the xy plane. Your f of x is now a positive value, and g of x is also positive. Sometime later, your f of x is quite positive, g of x is quite positive as well. There you are. So if you plotted every point in between t0 and t1, and even some beforehand, you will see you're tracing a curve in the xy plane that goes in this direction. Okay, because as t's are increasing in that direction, that's where your curve is going. Now, how in the world do you represent these in 3 space when you're only drawing on a 2-dimensional sheet? It makes it quite difficult. Okay. All right. Your first value, the vector r, when t is equal to t0, it appears here, and I think it's true, that your x value, your f of t, is here. You have no y value. Your g of t is 0, but your h of t is up here. So that then gives you your first vector here. Come out the x-axis and up the z-axis, so you're in the xz plane right there. But then your next point, when t is equal to t1, your r, your x value looks to be awfully close to the same, maybe not quite, a little bit further out. Your y is certainly changed, and your z is also changed. So now you're coming out of the board and coming up to you and rising at the same time. And then when t is equal to t2, your x is reduced. It went slightly larger here and then reduced to 0 here. Your y has gotten quite a bit bigger, and your z probably has come down just a little bit, maybe even a little bit less than it was at t0, and there is your space curve C. Now, I'm sorry, I've got to sneeze. I'm trying not to. Okay, sorry about that. It was warming up outside. I don't know why it's suddenly getting cooler here. I think I might know. Our cleaning lady's here. I think she turns on the AC, so sorry. Sorry about that, folks. Okay, so this is a curve in the XY plane. This is a curve in space. That's coming out at you and then going back in toward the board. Okay, just looking at them, they both look like they're in the plane because they are. Okay, they're on a plane, but you have to get that third dimension visual in there, and that's why they put the little marks down here and then in the XY plane and then draw up to the Z space. Okay, now again, the arrowheads show the direction of increasing t. Here it is in a plane, there it is in space. So you're increasing from t0 to t1 to t2, from t0 to t1 to t2. Okay, now that gives you the curve's orientation by pointing in the direction of increasing values of t. Unless stated otherwise, the domain of a vectored value function R is considered to be the intersection of the domains of the component functions x, f, g, and h. Okay? Now, I don't know if that's saying a lot to you. Here's what they mean by that. If your f function has some limitation of its domain, and we're going to see a couple coming up really soon, but the g function has another limitation or a different limitation, and h function may have no limitations or yet more limitation, then the intersection would be the values of t that fit all three of those. Okay, so here's what we've got. For instance, here is your function. R of t is log of ti plus the square root of 1 minus tj plus tk. Okay, now your log function here can only be defined from 0, not counting 0, but from 0 to positive infinity. That's the only values your t can take on, because you can't take the log of a negative number or even the log of 0. So this is from 0 positive. However, your square root of 1 minus tj, the values for t for that one can only be from 0, well, let's see. I'm going to actually write it out for you rather than just saying it. Okay. Okay, the domain here, where in the world is the pen? There it is. Okay. The domain here, the t has to be from 0, not counting 0, to positive infinity. Okay, here, your 1 minus t has to be greater than or equal to 0, which means that 1 has to be greater than or equal to t 1 has to be great. The stinking clip has come off again. Just makes for such a pain in the neck to try to keep the wires from getting tangled up. So t has to be less than or equal to 1. You can reverse that and write it that way. If I could find my pen. Here it is. Okay, you can write that this way: t is less than or equal to 1. Okay, now this t, any real value. So this t is going from minus infinity to infinity. Now I know I changed my notation there, but all real values, no limit there at all. Well, this tells you t has to be greater than 0. This tells you t has to be less than or equal to 1. This tells you t could be anything. So the intersection of those three domains would be from 0 to 1, closed like that. Can be 1, can't be 0, can't be any negative number, can't be anything beyond 1. Okay, so there's your domain of this vector value function. Can't go outside of that. Okay, so you're stuck within that limitation of t. Okay, that's called the intersection of the domains of each of your three component functions. Okay, now they skipped example 1 unless I missed it somewhere there. So let's go back and do example 1. We'll do it on the, let me back off 1 here and go to the whiteboard. Now, and clear off this. Does anyone need that any longer? Okay, clear that. Now for some reason I have to move all this taskbar and everything else around. I had it all moved, and when you start something new, it all goes back to where it was before. Okay, well, that seems to have been in place pretty well there. Okay, example 1. I'm going to have to get the book in my lap here, and we have what, 5 minutes? I believe that's right. Let's see if we can get example 1 done in 5 minutes. Sketch the plane curve represented, by the vector value function r of t, that's a vector, r of t is equal to 2 cosine t in the I direction minus 3 sine t in the j direction, where t is between 0 and 2 pi. Okay, now this is going to be a plane curve, so all we need is the xy axis. If I could find my pen. There it is. Okay, there's going to be the vertical axis. Here's going to be the horizontal axis. Okay, now I'm going to pull a little seniority on you here. I know that looking at this, cosine t goes between plus or minus 1, sine t goes between plus or minus 1, so therefore your x and your y values are going to be, the x value is going to go between plus or minus 2, and the y value is going to go between plus or minus 3. So let's get that drawn in now. 1, 2, 3, negative 1, 2, 3. Then we'll do the x here, 1, 2, 3, and negative 1, 2, 3. We don't need those 3's. I just drew them because I drew them on the other. All right, so let's let t equal 0, its initial value. Cosine of t is 1. 2 times 1 is 2. So 2 in the I direction, there's where that would be, but when t is equal to 0, sine of 0 is 0. Minus 3 times 0 is still 0, so your j is 0. So there is your first value. Okay? Now, let's go t is equal to pi halves. That's a nice one to do. When t is equal to pi halves, your cosine of pi halves is 0. So it's 0 on I, and here you'll have sine of pi halves is 1, but there you have a minus 3, so you're down here, y is equal to minus 3. So it looks like that this has gone, and I'm just going to sort of fill in the gap here. It's gone to something like that, okay, in that direction, increasing t. So let's go to the next one. We use t equals 0, t equal pi halves. Let's do t equal pi, okay? Okay, when t is equal to pi, cosine of pi is minus 1. Minus 1 times minus 2 is minus 2, so your x value is minus 2. Your y value, sine of pi is 0, minus 3, so there it is. So now we've gone around to here, okay? And then when you do t is equal to 3 halves pi, cosine of 3 halves pi is 0, so your x value is 0, your y value is plus 3, because the sine of 3 halves pi is minus 1 times a minus 3 is a plus 3. So now we've gone up to here. Whoa, that's not doing well. And then, as you might guess, you've gone full, I want to say full circle, but it's not a circle, full ellipse. You have just drawn an ellipse, because when it's 2 pi, you are 1 period further over here, 1 period further here. You got it. Okay. Yeah. Okay. And that is your ellipse. So you are going in this direction. You don't have to draw all the arrows in here. I just sort of like to remind myself in each quadrant which way I'm going. All right, any questions on example 1? And that did take us right up until 1:55, okay, which is when class ends. And if I can find my pencil, we'll be beginning next time with example 2, okay, on page 821. Now, we didn't get a lot done in 12.1, but let's see how far we get. I think you can do any of the odds 3 through 9. They're all at Calc Chat. 3 is at Calc View. Okay? And maybe we'll stop there and pick up the rest of those next time. All right, any questions from either 11.6 or 12.1? All right, and like I said, sometime this afternoon, sometime between 4 and 6, hopefully, but if not, maybe after 6, before 10, I'll try to get your chapter 11 test out there for you, okay? And then based on that, get going. Now, let me just point it out to you, okay? We are in the month of November, okay? Which means we basically only have 4 weeks of school left. 3 of those are class time. The last one is finals time. Now, we have longer than 4 weeks left, but there is no school in the week of Thanksgiving. So we only have 3 weeks of classes left, and it may only be, well, yeah, so in other words, if you haven't submitted your research paper yet, please get those in. If you haven't submitted the first test yet, please get those in. If you haven't submitted the second test, please get that in, because I'm about to give you your third test, right? So please get in what you can, and we only have a short amount of time left, okay? Any questions? Okay, I'm going to try to get caught up on grading some. I've made some progress yesterday, but not nearly enough. So, but we're going to, oh, and one other thing. This is also bad news. Next Wednesday is Veterans Day. And if I'm not mistaken, that means there's no college that day. No classes, no nothing. Okay? The system is shut down on Veterans Day. So that's also come into play. That gives you one fewer day to work on things. Well, you can work on them during that time off, but no new classes that day. All right. Any questions? All right. I'm going to clear my drawings here. I'm going to stop the sharing here. Any questions, folks? Okay. So take care. Be safe this weekend. Looks like it might be a pretty weekend, but be careful. Be safe. Don't risk anything. Okay. We'll see you on Monday. That's all. We'll see you next week. See the rest of you, 3 of you later today, or 2 of you later today, and same 2 on, well, let's see, no, I guess so. Well, whatever. You know who you're going to be. Okay. And we'll see you, some of you, 2 of you tomorrow. All right. Take care. We'll see you next time.